This is Algebra Lesson 4-3, Patterns and Nonlinear Functions. A nonlinear function is a function whose graph is not a line or a part of a line. Graphs that are nonlinear look something like this. You could have a graph that looks like a V graph. You can have a graph that looks like a function that looks like this. You can have a graph that looks like this. It's just a non-linear graph, not a straight line. Okay? So just like linear functions, nonlinear functions can be represented using words, equations, sets of ordered pairs, and of course a graph. And of course down here I've put some pictures of a linear function and those that are not linear. A linear function is a line, hence the word linear comes from the root word meaning line. And then you have nonlinear functions. This first one here is what we call a parabola. It's an equation to the power of 2, x is squared. This one in the middle here is part of either a sine function or it's a cubic function, x to the power of 3. And this last one over here is an absolute value function, which we will get into all three of those types of functions sometime this year. Okay. Classifying a function as linear or nonlinear. A lot of times if you look at the table, you can't really figure out whether or not it's a linear function until you actually graph the points that are on the table. So the table below shows the function a of the original area of a piece of paper that remains after the paper has been cut in half n times. Graph the function represented by the table and then tell if it's linear or nonlinear. So basically what we do is we have a regular piece of paper. If you make one cut, and every time you do, you cut it in half, you have half and half. The original area is now half of what it was to begin with. If you make 2 cuts, it's now then a fourth of what it started out with. If you make 3 cuts, half of a fourth is an eighth. If you make 4 cuts, half of an eighth is a 16th, and et cetera, et cetera. So if I was to graph these particular points on a set of x and y axes, of which I've numbered, so we have the x-axis, which is 0 through 5. It's called n, and it's the number of cuts. And you have your y-axis, which is a fraction of the area remaining. Notice how it's going up by, this is an eighth here, so then you have a quarter. Then you have 3/8 and 4/8, which is a half, 5/8, 6/8, which is 3/4, 7/8, and 8/8, which is 1. So if we have 1 cut, our area remaining is 1/2. So let's graph that. So we have 1 1/2, which would graph right here. And then we have 2 1/4, so go over 2 and up to 1/4, which is here. If we have 3, we have 1/8. Well, 1/8 is here. And if we have 4, we have 1/16. 1/16 is halfway between 1/8 and 0, so it's going to be like right here. And as we can see, this is a kind of curving graph. It's not a straight line. If I was to try to draw a straight line through this, if I was to take my graph and I try to draw a straight line, notice it doesn't go through all the points. It misses quite a few of the points. Therefore, it is not a linear graph. It is a nonlinear graph. If we were to graph it with a line or to try to connect the points, you would connect them with what we call a smooth curve, trying to get all the points in the curve. So it looks something like this. Okay? You don't always have to connect the points because you connect the points when it's considered to be a continuous function, and you don't connect the points when it's considered to be a discontinuous graph or a discrete graph. We will talk about that, a continuous graph and a discrete graph, next lesson, but that's a good introduction to that particular part of this. All righty. Representing patterns in nonlinear functions. It says the table shows the number of calls made in a phone tree during each level. Identify the pattern to complete the table. Represent the relationship using words, an equation, and a graph. Okay, if you don't know what a phone tree is, it basically says this. Okay, here I am right here. I make a call to person A and person B. Person A then makes a call to 2 people, and person B then makes a call to 2 people. These 2 people then make a call to another 2 people, and these 2 people. That's why it branches, continues to branch out, and that's why it's called a phone tree. Okay, so basically that's what we're looking at here. So if you look at the number of calls, if on the first level only 2 calls are made, call to person A and call to person B. And the second level, you'll notice, okay, if we can call these C and D, and then E, and then F, you'll notice that we have 4 calls are made. It's 1 to C, 1 to D, 1 to E, and 1 to F. And then when we get down to it, when we get to the next level, you have 8 calls. 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so if on the 4th level, you'll notice these keep doubling. 2 goes to 4, 4 doubles to 8, 8 will double to 16, and 16 will double to 32. Okay, so on the 3rd level, we have the 3rd level, there's 8 calls. The 4th level, there is 16 calls. And the 5th level, there's 32 calls. Okay, what we are going to try to do is we're going to try to figure out a pattern after we've actually graphed this. I think we'll figure out the pattern after we graph it because it might be easier to just graph it first. So the first thing I'm going to do, if I'm going to graph my graph, it's always good to label your x and y axis. Always, always, always label your x and y axis. So there's one axis. Wow, that's not a very straight line. I'll fix that in a second here. There's my second one. Let me move this back to where it belongs. Nope, it doesn't want to move right way. Too fine. Shift down. There we go. So here's my x-axis. Here is my y-axis. I don't need the negative portions of the graph because I can't make a negative number of phone calls and I can't have a negative number of people. I can't have a negative number of levels of calls. And first level is positive. I will call 2 people. That's positive. Doesn't matter if they pick up. It's just how many people did I call. All right, so this is the level here. And this would be the number of calls. And it's really hard to label sideways. There we go. So 1, 2, 3, 4. In fact, actually, what I think I'm going to do, that's fine. 5, 6, 7, 8, etc. Okay. Number of calls. I'm probably going to go up by 4s because everything goes up by 4s. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Nope, I'm going to go by 4s. So this is 4. This is 8, 12, 16, 20, 24, 28, 32, 36. Because you need to go by equal increments. The increments that you go off of on the x-axis do not have to equal the same as your y-axis when you're not using all 4 quadrants. When you're just using quadrant 1, as long as you're equal, on my x-axis I'm counting by 1s, and on my y-axis I'm counting by 4s. That's perfectly allowable as long as you're only using quadrant 1. Okay, if you're using all 4 quadrants, you can do that. It can just get a little hairy sometimes and make your graph look pretty funny. Okay, so, and it's always good to label what you're graphing by so that people know. Don't assume people will automatically know what you're counting by. So my first order pair is 1, 2. So 1 here, 2 is halfway between 0 and 4, so it's right there. My second order pair is 2, 4, so 2, 4 is right there. Then I have 3, 8. So 3, and then goes up to 8. And then I have 4, 16. 4 jumps up to 16. Notice how much it's jumping all of a sudden. And then 5 goes up to 32. Okay, so this is definitely not a linear graph. It's what we would call an exponential graph, actually, because it's growing quite quickly. It's growing, it's doubling every time. Okay, I'm going to erase my phone tree for a second because I need this workspace here. So we've graphed it. We need words in an equation. Okay. So I need to figure out what the pattern is here. What is the pattern between this number and this number? Because if I'm looking at 1 to 2, you're like, oh, well, 1 times 2 is 2, 2 times 2 is 4, but 3 times 2 is 6, so that doesn't work. 4 times 2 is not 16. I need to figure out how do I get from 4 to 16, how do I get from 3 to 8, how do I get from 2 to 4, how do I get from 1 to 2? And you think about it and you're like, oh, I have no idea. Well, remember, everything started with the level of the first person made 2 calls. So can I do something with 2s here? Like you might look at this and say, oh, let me see here. Let me erase my red really quickly in here. And you might say, well, 2 is the same thing as saying 2 times to the first power. 4 is the same thing as saying 2 to the second power. 8 is actually 2 to the third power. 16 is 2 to the fourth power. And 32 is 2 to the fifth power. So I can look at this and go, oh, 2 is very important because everything started with those first 2 phone calls. So I can look at this and say, I see here, my pattern is that the number of calls made at a level is equal to 2 raised to the level. Okay, so the number of calls made So the number of calls made is equal to 2 raised to the power of the same power as the level. So to write that in equation form, it would be that y, which is the number of calls, is going to equal 2 to the x power, because x is the level that you're on. So we have represented this using words. That's the big phrase of words I used. An equation, which is y equals 2 to the x, and the graph, which we have over here to the right. All right, writing a rule to describe a nonlinear function. Okay, it's often more difficult to write a rule for a nonlinear function than it is a linear function. This last problem we just did might have been a little bit more difficult to figure out the rule. This one that we're going to do right now may be very difficult to figure out the rule. It says, what rule is represented by the ordered pair 1, 1, 2, 8, 3, 27, 4, 64, and 5, 125? So let's make a little table here. Let's make x and y table. If x is 1, y is 1. When x is 2, y is 8. When x is 3, y is 27. When x is 4, y is 64. And when x is 5, y is 125. Some of you, this might be really, really easy. You might look at it and go, oh, I know what this is. I know what this is really easily. Others of you are going to look at this and go, I don't have the slightest idea. To get from 1 to 1, you multiply by 1. To get from 2 to 8, you add 6, or you're like, how do I multiply it? What do I get? 2 times what equals 8? 3 times 9 is 27. 4 times something is 64. 5 times 25 is 125. So you might start looking at this going, okay, 2 times 4 equals 8. This might help. 3 times 9 equals 27. 4 times 16 equals 64. 5 times 25 equals 125. Well, think about this for a moment. 4 is the same as 2 times 2. So this would be 2 times 2 times 2 because 4 equals that. 9 is 3 times 3, which means this is 3 times 3 times 3. 16 is 4 times 4, this makes this 4 times 4 times 4. And this one is 5 times 5 times 5. So maybe now you can look at this and say, oh, well, obviously 1 is 1 times 1 times 1. Therefore, the pattern to this one, you might look at it and say, oh, it's just x to the third power. Because 1 to the third is 1. 2 to the third is 8. 3 to the third is 27, because there's 3 3's right here. 4 to the third is 64. And 5 to the third is 125. So the pattern, the rule that is represented by this set of ordered pairs is y will equal x to the third power. So there's your pattern. Some people may have seen that really, really easily, and others may have taken quite a while, and some of you may only have seen it once I showed it to you. Okay. Every person's going to see the patterns a little bit differently, and some people are going to find them faster than others. Just don't give up. Keep trying something. Look at something, try to break it apart into things that you can break it apart into, and see if you can figure it out. All right, your closure question for this lesson. How can you describe the rule for a function? And we've talked about this entire thing. What are the different ways that you can describe a rule for a function? That's what this question is asking.